Our technique, we talked about like the disc method, which was just basically a cross section with a circle. Area of circle is pi r squared, and we integrated that. Then we talked about if it's hollow in the middle, then that's more like a washer. So we did the washer method, which is basically the outside circle minus the inside circle, and integrated to get the volume. The final technique that we're going to look at is cylindrical shells. This method, some of the problems that we've already done could have been done with this method as well. So it's not necessarily like the disc and the washer, and you had to pick one or the other. This one sometimes could be used in place of one of those, so it's not necessarily a right or wrong, you have to pick the right one. On the test or quiz, this one is not my biggest emphasis, it's kind of the last little piece. So I would probably put a test on the quiz and say, do this one by shells. The others, I would just say, find the volume. So you use whatever method is necessary. So this option can help on some of those more difficult questions. If I gave you something like the function 2x squared minus x cubed, okay? And I wanted the region bounded between that and y equals 0. Okay, it's a little bit harder to integrate that when I start rotating it around the y-axis. Because as I rotate that around the y-axis, I'm getting, something like this. But it's a little less clear. The outside and inside, just a little bit harder to find these x values as we go along. And so that's a situation where shells can be more helpful. Essentially, to do this volume, we're looking at a shell. So volume is circumference, distance around the circle, times the height times the thickness. Right? Think area of a circle we know is pi r squared. This one is finding it by doing the distance around, like kind of think more length times width times height type thing. So circumference of a circle is 2 pi times the radius. And then our height, so our f of x. Okay, that would be our function. And then to get the volume, we integrate that. So we're basically integrating that area as we move around. Essentially, there's a whole way to derive this. It's talking about basically finding the average radius at any given point in time, and that's how this is derived. This is just kind of showing us essentially what's happening. If we're trying to find this overall thing, we're breaking it into smaller pieces. And if you wanted to find the volume of this, you could think like, okay, let's think just two-dimensional for a moment. If I took a soup can, right, and the label on it, if I unfold that label, I have a rectangle, length times width. When you throw depth into it, that's where the third dimension comes in. The length of that rectangle is the circumference of the circle. That's where the 2 pi r comes in. Okay. So, for example, and I did have a couple typos on this. I printed or notes before I realized it. I think yours says an extra equal to there, and I meant for that to be a minus sign. So, we'll have to correct a couple of my mistakes as we go through. Find the volume of the solid obtained by rotating around the y-axis, the region bounded by the 2x squared minus x cubed and y equals 0. So that's the one we were looking at right here. Okay, and my picture was really terrible, but as you look at this, it's not even like a true donut. It's not completely hollow in the middle, right? It's kind of coming in towards it. You're getting this three-dimensional shape. So if I wanted to use my other technique, since we are rotating around the y-axis, we are actually just going to work in terms of x. This is a little bit opposite of what we were doing on the disc and washer methods. But rotating around that y-axis, we are going to work from our x's here. So if I wanted to find my x's, I need to know when my curves meet. gives me 0 and 2. And the reason we're working in terms of x is because if I cut this and unfold it, so when I'm rotating around the y, I have those x values measuring it if I unfold my circle. Okay, so to do shells, we're doing 2 pi times the radius. If I'm working in terms of x, my radius is x. If I'm working in terms of y, my radius is y. Times my function. So that is the shell method, just 2 pi x, and then our function is 2x squared minus x cubed. Again, it can be a little bit hard to distinguish which methods use when, so I would specifically say do this one using shells. And I would not probably put a bunch of those on there. I think the other methods are a little more intuitive for us right now. And if you have to go on and take Calc 2, you'll do much more of this stuff. We're just kind of dipping our toes in the water right now. So if I multiply that out, I get 4 pi x cubed. That's 2 pi. Actually, could I just pull out that 2 pi? Do you guys care? There's no reason to drag that along. All right. What is the antiderivative of 2x cubed? Minus the antiderivative of x to the 4th. And we are evaluating from 0 to 2. So put in 2 to the 4th is 16 times the half is 8. And this 32 over 5. So put in 0, I get 0. 40 minus 32 would be 8/5 times 2 pi, so 16 pi. So when we're doing this, volume is circumference times height times the thickness. This is essentially our circumference. Okay, that's how we measure if we unfolded that, how long is it? This, our function, is how we are measuring the height. And this dx is the thickness. You know, we can see as I unfold it, it's thicker at different points, right? That thickness is variable depending on where we're at. If we look, you know, here it's much thicker than it is when you get up to the top. So that thickness is changing, so that's the dx portion. All right. What questions do you guys have right there? Let's look at some more. Okay, all of these we're doing by shells. So find the volume of the solid obtained by rotating about the y-axis. The region between y equals x and y equals x squared. So y equals x we know is just a line. X squared is a parabola. So we're looking at this region. Rotating that around the y-axis. It's going to look something like this. Now, would I have to use shells to find this type of volume? No. Couldn't we use like the washer method here? Outside minus inside? Absolutely. Okay, this is just another technique for some more complex type problems that sometimes couldn't be solved another way. All right, so if I were this by shells. We still need to know where these curves meet. So that's at 0 and 1, so we're going to integrate from 0 to 1. Shells says we do the circumference. In this, if we're rotating on the y-axis, we're going to work in terms of the x's here, because when I unfold it, we could measure on the x, the length around. So it's 2 pi x. All right, my function. All right, if we were going to take a shell here, so it's saying like instead of just looking at a circle, if we did this 3-dimensional shell and I took that slab, the height of this is the distance between these curves, right? So that would be x minus x squared, the higher one minus the lower one, to get how thick that slab is. Again, if you mess up that part, how will you know? You'll get a negative at the end, so you can just say, I know that should be a positive, I'm doing the absolute value of it, and that would be my true volume.
So for the thickness, we're not finding the distance between the outer shells and the outer.
Right. So this is different than how we were doing it before. But it's saying basically if I took a bunch of little shells here, like 3-dimensional pieces, and found their volumes and put them together. So the height of those is the higher curve minus the lower one.
Okay.
And that's again why we're working in terms of x versus we were doing the washer method with this, we would probably be working in terms of y, because we would have a clearer high low point.
Yeah.
So we could take out our 2 pi. So 1/3 of x squared is 1/3 x cubed minus 1/4 x to the 4. So that's 2 pi times 1/12, or pi over 6. So again, like this isn't the only way to solve the problem. We're just using a different technique. And if I want you to use it, I will specifically say use the shell method here. So okay. Let's try a couple more. So I want the volume of the solid obtained by rotating around the x-axis. The curve y equals x to the 1/2, so the square root of x. But I am rotating this around the x-axis. Okay, would I have to use shells? No, this is a very straightforward one that if I were setting up using the disk method, I would just go from 0 to 1. All right, so, but because I specifically said let's try doing this with shells, we have to change our approach from what we were doing before. All right, we already know we're going from 0 to 1, but here's the thing, if I'm rotating this, then if I took a shell, okay, so if I took a chunk here, the circumference, when I unfolded that, it would be measured in terms of y, wouldn't it? So if I take your soup can, flip it on its side and unroll it, you have a highest and lowest point. So it's in terms of y. So we need to work in terms of y on this one. If you want to solve this for y, that means y squared is equal to x. Now we're lucky the 0 and the 1 don't change. If I plug in 0 for x, I get 0. If I plug in 1 for x, I get 1. So my circumference is 2 pi times the radius, which we are measuring our radius from here to here, so that's in terms of y, because it's the height. All right, and then we have to put what in here? What comes next? We have this is like our circumference. So then we need to think about the shells themselves and how we measure the height of those given shells. The height is like the depth of this shell. I can't necessarily just say, if we're working in terms of y, we're going to have to think of this a little bit different because we have a clear stopping point. We're going from y equals 1 here. So the height of these shells is 1 minus our y value. Okay, so it's a little bit different. So it's 1 minus our function to get the actual height of this. Is this an easier option than this method? Not at all. This is way more complex, okay? There are times and places. This is a problem that I would never specifically say you have to do the shell method because it makes it way harder. So I'm just trying to illustrate here, like, we have all these options, but it depends on the problem, which one is better, because this is definitely less clear that our height has to be the 1 minus. All right, so we could take out our 2 pi. Y minus y cubed. Antiderivative of y would be 1/2 y squared. Antiderivative of y cubed. 1/4 y to the 4th. Pi over 2. So this became more complicated because we were rotating around the x-axis. The y-axis is much simpler on these. All of your homework questions are going to be around the y-axis, so they'll be more like the first couple, pretty straightforward ones. Okay. Last problem. I want the volume obtained from this rotating the region bounded by y equals x minus x squared and y equals 0 about the line x equals 2. All right, x minus x squared, that's like an upside down parabola. If I put in 0, I get out 0. If I put in 1, I get 0. So looks something like this. So I am talking about this region right here. And I'm rotating that around x equals 2. So as you do that, we get this weird looking shape here that I can't draw. I just can't, I'm sorry. Bryson, you may need to illustrate for me on that. But it's kind of like a ring of sorts with varying width. It's skinnier at the top and wider as it goes down. Okay. So if I am looking at this, we know we have to integrate we're working in terms of, we're rotating around x equals 2, which is kind of like rotating over the y-axis. So we'll just work in terms of x's. Our x's just went from 0 to 1, right? That's when we found it was the curves met. So we have 2 pi times the radius. Now the radius is a little bit different here because I'm not rotating around the axis. So my radius isn't just x, it's going to be 2 minus x. It's the distance from 2 back to our point. And that's because I did not rotate around the axis. Okay, then the height of these shells is just the function, the x minus x squared. Okay, that function gives the height at any given point when I look at my shell. So if I FOIL, antiderivative of 2x would be x squared. Antiderivative of 3x squared, x cubed. Antiderivative of x cubed would be 1/4 x to the 4th. Two pi times 1/4 is pi over 2. Just to kind of clarify a little bit on number 2. We're rotating around the y-axis, so we're going to be working in terms of our x. So that's what the 0 and the 1 are just telling us our starting and our stopping points. If we look at this, if you put in a 0, you get a 2. If you put in a 1, you get 1. Now we are bounding that with y equals 1, so I'm only talking about this region. That's what I'm actually rotating. So when I set it up, 2 pi, my radius, if I were to take a slab, my radius is still my x value. But what's a little bit different is the height. Okay, so if you were looking at a slab and you were measuring the height of it, you're going to have to go from here down to here, right? So it would just be top minus bottom. So if it's between two curves, just like if we were doing the washer method or something, you just do the top one minus the bottom one. So my top is the negative x squared plus 2 minus the bottom was just a 1.